Today we're going to see the plane motion of rigid bodies and energy and momentum methods as they apply to vehicle dynamics. So let's consider first the basic principle that says this is the principle of work and energy that says that the work um, the kinetic energy at the position 1 of the body plus the work done by the external forces should be equal to the kinetic energy at the second position of the body. So in this case, it's important also to get a definition what actual work is. T1, T2 are the initial and final values of the kinetic energy. And U1, 2 is the work done by the external forces. So if a vehicle goes uphill, it follows this principle that the kinetic energy on the final position has to be the initial kinetic energy plus the work done by the external forces. In this case, it's also important to indicate that the work of the force F applied on a body is the force in the direction of travel. So if the force is applied at an angle alpha, the amount of work is going to be done not by the vertical component but by the horizontal component, and that is going to be F times cosine of alpha. If the work done, if the body is in rotation, it follows the same principle that the kinetic energy of the body is the kinetic energy originally plus the, in this case, the work done by rotational conditions. In this case, the moment times the distance. So, this would be the summation of the moments times the distance. So the kinetic energy of a rigid body in plane motion, remember what plane motion is translation plus rotation. So when a vehicle rolls over, not only is translating, but is rotating about the center of mass. It's the same principle as if you have it with a football. The ball follows a parabolic trajectory, the center of mass does. But the ball goes tumbling down around its own axis. So that thing is in plane motion, meaning a combination of translation plus rotation. So if you calculate the kinetic energy, it's going to be 1/2 of mv squared for the translation plus 1/2 of I omega squared for the rotation. Right? The kinetic energy of a rigid body might be separated like in the two parts. One, the kinetic energy associated with the motion of the center of mass, and the second one, the kinetic energy due to the rotation associated with the rotation of the body. So you could see the comment in here in the middle that says for a rigid body rotating about a fixed axis through O with an angular velocity, of course, t is going to be 1/2 of I, or the moment of inertia, and the square of the angular velocity. If the forces are conservative, they don't, the external forces that do not do work, the sum of the kinetic energy plus potential energy at the position 1 is the same as the kinetic energy plus potential energy at the station 2, at the final position. This is called the principle of conservation of energy. Also, this slide contains a slight definition of what power is. The power is the amount of work per time. We could just put it that way. The amount of work per time is power. So you have du dt, which will be m d theta dt, or m times omega is power. Now, this is an interesting slide because it is very important. We need to look at what the momentum of the system is at the position 1 and what the momentum of the system is at the position 2. So, in this case, for this slab, we have this slab like in the plane of the screen. The system momentum plus the system of external impulses is equal to the momentum after. Okay. So you have in the picture, you see how an unbalanced set of forces, as seen on the left-hand side, is equivalent to the dynamic forces. The dynamic forces in this case, mass times acceleration of the center of mass, and in rotation, the moment of inertia times omega. So a great deal of problems can be solved by applying this basic principle. What we are saying here is that the summation of the forces acting on the body equals to the two resultants of motion. So this is the resultant after, it was a prior motion, the resultant, or the new motion, the momentum. Okay. Now this is important. Not only the momentum is changed, that the car was traveling, in the direction it was traveling. But it also produces rotation about the center of mass. So this can be expressed by drawing these three diagrams. And if you have the momentum afterwards, it would be equivalent to the mass times acceleration of the center of mass and mass times rotation about the center of mass. All right. So we need to establish principle. So this is m times b1 plus I times omega 1 is the momentum of translation and rotation of the first mass, and over here you can see that this is the sum of the external impulses. So this is F times dt. So, and then this would contribute to the vector, to the second one. So here we have the idea that the summation of the forces about the center of mass before and after the collision. So you have mb sub 1 and I omega 1 in the, and the impulses is going to be F delta t or FDT. That we get the one on the side. And now we have a little bit more in detail the impact. So like I said, these are the basics that we want to examine here. You have before the impact, this is traveling like this is traveling like this. And you can see the position of the vectors afterwards. It's important, and this is what we will do in the next class in a lot of detail, is how do you establish those directions of the vectors first. And then after the collision, how do you establish the directions? Usually what happens is that after the collision you have pictures, you have people who do measurements, and ultimately there's a technology for doing laser scans that maps out the three-dimensional scenery. So that's the scope of what we have to work with. So in this case, I use this expression. V primes are for the velocities after the collision. V prime minus VA prime divided by E times velocity of A with respect to n minus the velocity of B with respect to n. Okay. So do you see that letter E in between there? This one is called the coefficient of restitution. You remember we talked about this in a prior lecture. We're trying to do it with the red car impacting the wall and bouncing back 10%. More or less, that's about right. So if the car hits the wall at 35 miles an hour, and afterwards it moves with 3 miles an hour, then you, you can calculate the coefficient of restitution. So it makes sense that if the restitution is, is a fraction of the entire E times P sub A minus P sub N. Here you have the other analysis of the before and after the impact for these two bodies. But what is key to this whole thing is the fact that the number, the C number is the coefficient of restitution. It's an indication of how plastic or how elastic the collision fue. How the collision, how is the collision, elastic or or plastic? Elastic meaning bounce completely and energy is conserved. When inelastic means all deformed, all energy lost. So we have those are basic principles for the um, kinematics of a system of particles with contact forces.